Like I got home. No, I got home and I pulled everybody into the room. I was like, I had my hair up again, and I was like, look guys, this is what I did. I pulled my hair down. I was like, holy shit. And then his dad was like, oh, you cut it off. How much? I was like, it's 16 inches. Shelby was just like, I was like,
You wouldn't expect like 60 or 70. Yeah, exactly.
Exactly.
he got his haircut, but he got mad because like, oh, it looks stupid.
No, I told him outside if there's anybody outside,
Well, then he got mad at me because he's like, well, today, okay, we have a very honest relationship. So today, we were supposed to meet in his room. No, he decided to abstain. Yeah, so we were going to meet in his room today, and he got mad at me because we were talking about because there was free food involved. I got to also, he's not interested.
maybe a couple of them.
Oh, I want to.
Couple of beef injections.
Hey, where are you going? But you know this was my flip-flop broke.
To the moon and maybe one or two other objects. It's nice and bright on campus, so you can't see a whole lot. So, to begin with, is always the question I get around Christmas time, especially right after Christmas. I get a call from some mom or dad that I bought a telescope for my kid, and we set it up in the backyard and looked at the moon. It was really cool, but we can't see anything else in it. What's wrong? And I think, well, okay, let's see. Where are you pointing it? Oh, I was just pointing at stars and stuff. Well, a star through a telescope is a point. It looks like a star. There's no difference between the telescope and what you see with your bare eye, other than it maybe looks a little brighter. But that's about it. It's still a point. So if you want to look at some of the interesting things like planets and stuff, you have to know where they are. So, how do you know where things are here on the Earth? Go to someplace interesting. Let's see, the Colosseum in Rome. How do you find that place? Google Maps, Colosseum, Rome. Oh, okay, it says it's there in Rome, but maybe I want to zoom out and see where Rome is. Okay, it's in Italy. Okay, maybe I want to zoom out some more and see where Italy is, because I don't know where that is. Oh, it's in Europe. So it's a matter of maps and scaling down. A lot of times, if you're using paper maps, you start with a large scale to find first where it's at in the larger scale and then zoom down. Same way with the sky. You want to look at something in the sky, where's something interesting to see in the sky, you start with maps. And the first ones to start with are these. They're called planispheres. And they come in cheap variety here. Cardboard that if you take it out at night in Tennessee, especially in the summertime, lots of dew formation. At the end of the night, you've got a wad of pulp. You pick it up and it just kind of shreds out on it. So But this only costs like $2. And in fact, you can download templates for it online and make one yourself for the cost of the paper. So they're kind of nice, but nicer to have something bigger. We've got 3 different kinds. I like these that have white sky and black or blue stars with blue stuff here. They come in all sorts of different varieties. This has black sky and white stars. I like that one better. I like this one better, mainly because it's nice and big. They also come from different latitudes because where you're at on Earth, of course, is going to make a difference in what you see in the sky. So this one's for, where does it say, 30 to 60 degrees north latitude. So you dial up your date and time. You have to be able to dial the date and time because the sky moves around us. So let's see, we're in November, where are we at? All the way over there, and we want to go to about, we'll call it 7:30 on the 19th of November, somewhere around there. And that tells me what's up in the sky. So I would face out, hold it up like that, and it tells me that bright star over there is Vega, and the one over there next to it is Deneb, and the one over there lower down is Altair. So it tells me the names of the bright stars, constellations, things like that. Think of a flat map of the Earth. Are you going to find Clarksville on a flat map of the Earth? Nobody?
No.
Yes, no? Probably not. What you're going to find, you might even not see Nashville. Probably you'll see Washington, D.C., Chicago, New York. You'll see the big cities. You're not going to see the small cities. Certainly not going to see the smaller towns. So these are like that. You're not going to see all the fine details. You're just going to see the bright stars, things like that. So, but they're very nice. Like I say, they do come in different latitudes. Had a student bought one year, wanted to learn the sky, and took it out, dialed up his date and time, kept holding it up, couldn't find anything. And finally, he brought it to me and said, Doc Wagner, I can't figure out how to work this thing. I keep dialing my date and time here, but I don't find anything. And I looked at it and looked at it, and then I looked up at the stop and it says, Southern Hemisphere Edition. So I said, yeah, you need to move to Australia. So I bought it from him because I felt sorry for him. But these things aren't that expensive. These are like maybe $10, $11. This big one here was only with shipping. I think it was like $21, $22, something like that. So they're not all that terribly expensive. I like these because they're laminated plastics, so they don't let dew form, or if you get dew form on them, you just kind of wipe them off and they're okay. Not like the paper ones that fall apart. So that's kind of the first step. It's like using a globe. It's not going to find the smaller details, the little things that you're interested in, but it will give you kind of large scale stuff, show you where the constellations are. And some of these telescopes I'll talk about here in a minute have what's called go-to capability, but you have to initialize them first. And they always want to point at the star. They want you to point the telescope at the star Arcturus. And you scratch your head and say, Arcturus? What's Arcturus? It's a star, obviously, but where is it? I don't know. Get your planisphere out. You can find it on your planisphere, I guarantee, because it's one of the bright stars out there. Those are kind of the first step. The next step is you want the fine details. Where is it something interesting to look at? You can get your little booklets like this. They give you just maybe a couple of constellations, a little map with those and their stars around it, and then a little bullseye target. And you point the bullseye target, you use your Telrad, it's one of these things I'll talk about here in a second, has a little bullseye on it, and you point it at the area you want, and you look through your telescope and you see something. This one doesn't give you a picture of what you're going to see. It does give you a description down here. So hopefully you'll see it. This is a M4 is a cluster, 8 to 10 stars in a line, very resolved. One of the closest globular clusters to us, and it gives you things like this and all that. These are nice. A lot of the interesting stuff up there, and for those of you that are doing the dark sky alternate, you'll find lots of M objects. M stands for Messier. Messier was a French astronomer who, at the time he was observing in the late 1700s and early 1800s, he was basically in downtown Paris. In 1790 something and 1800 something, downtown Paris was pretty dark at night. Nowadays it's lit up all over the place, but at that time it was dark at night, so you could actually see a lot. But he was a comet hunter. He would try to discover comets. The way you discover a comet, you look for a little faint fuzzy blob in your telescope. You carefully note its position down on your star map, then you come back the next night, and the next night, and the next night. You see if that little fuzzy blob moved. If it moved, there's a good chance it's a comet, and you discovered a comet that gets named after you, and you maybe become famous, maybe not. You've heard of Messier outside the astronomer. But if it doesn't move, it's not a comet. Keep finding these things that were fuzzy blobs that didn't move. So he made him a list of these things that didn't move. So they're not comets. And that's what these are. These are the not comets. Not a comet in a whole bunch. But nowadays with better telescopes, we can see that they're nice clusters and nebulas and interesting things to look at. So they're the more interesting things to see. Especially objects, another one I like are the double stars. Oh yeah, you do. So like double stars. When you look through a telescope, pretty much what you're seeing is black and white. You see shades of gray, that's all. The way your eye works, you have two types of receptors. They're called rods and cones. The rods are actually pretty sensitive, and they see pretty much all the colors, mostly towards the blue end of the spectrum, but they see all the colors, but they don't distinguish what colors are what. They just see light. The others, the cones, are not as sensitive, but they are color sensitive. They tell colors. And so at night, when you're looking at faint objects, you're using mostly the rods, because the stuff you're looking at is not very bright. And so you see shades of gray. At daytime, when you get plenty of light around, you see colors. That's the cones in effect. But when you're looking through a telescope, if you look at stars, individual stars concentrate all their light at a point. And so it does hit enough light on one or two sensors to actually see the colors. And so double stars are nice to look at because they're one of the only places you can really see colors. You'll see two stars very close together. One of them may be kind of orange or red. The other one may be blue or purple or different colors to them. So you can actually see colors in the double stars. They're kind of interesting to look at because that's the only place you can see colors. That's the various star maps. You can also get maps in magazines and things of that nature. The ones I like, Astronomy magazine here at the front end of it, or in the middle of it, if I get it right here, is a nice star map for that particular month. And they have articles about things that are of interest, like this one was from November of this year, which is actually, they're like most magazines, they're a month ahead of time. So this was actually published in October. And when you looked at it in October, they had 100 years of general relativity, or all the stuff about Pluto, the New Horizon mission that flew by Pluto, and the images that are coming back from it. They're very nice. They have lots of interesting articles. I like that one a lot. There's also these things. These are called astronomical calendars. They're kind of, think of a farmer's almanac for the sky. It's got, more than just star maps in it. It's got all sorts of information about light pollution, about asteroids and comets and meteor showers and spacecraft and deep sky objects and space flight there. So conjunctions, that's when two things are really close together in the sky. So lots of other stuff besides just the monthly star map. They do have a monthly star map and articles about what's interesting to look at, where the planet's at, and all that kind of stuff. So that's very nice as well. This one also, I like this one mainly because it has a nice piece of artwork on the cover. And they do a new one every year, and it's always a new piece of artwork that looks kind of cool. So I think they also commission people to do the art, and usually has some astronomical theme to it, but it's kind of both there. Looks like Venus or something there. Power and stuff. Kind of interesting. So that's looking, finding things. So now you want to look through something and actually see it. good place to start with is something you probably already have, or a lot of people already have anyway. Binoculars. Binoculars are just two telescopes strapped together. They're not terribly big telescopes, but they're two telescopes strapped together. So they have a little zigzag in them always, because if you look through a telescope, if you remember the lenses in telescope lab, things were always upside down in your telescope. That's the way things are in telescopes. They're upside down. The zigzag on a pair of binoculars basically puts a couple of prisms in here that bring the image right side up. So you see people running like that rather than running like this. So, but the binoculars, you know, you basically hold them up. Now the problem is, if you're looking at something, the best place to look at something in the sky is when it's almost straight up overhead. So you got to do kind of the break my back limbo kind of thing, to look up like that. Easier is self-tripod. This is a camera tripod they've got, and a little attachment here that I can attach my binoculars to my tripod, crank it up. Now that's kind of low. If I wanted to tilt it up, look at something in the sky, let me rotate it around a little bit this way. That's still kind of low, but what I could do, get a stool. Sit down on the stool, look up through it. So it cranked up a little bit more, I think. So I could actually get it a little bit higher. But yeah, I would sit in a stool and look up that way. So this is just a camera tripod. You can go to, like, you know, yard sales and pick up one for $5 or something. But nice tripod and a nice pair of binoculars. Binoculars always have a number on them. These are 12 by 50 binoculars. The 12 is the magnification. Binoculars have some magnification. They're magnifying what you see. The 50 in this case is how big is the opening. In astronomy, of course, you're looking at faint objects, so you want a bigger opening. The bigger the better. I've seen binoculars that are 90, 120 millimeters. I call them the Schwarzschild, or the, not Schwarz, but the Schwarzenegger binoculars. You got to be Arnold Schwarzenegger to hold them up, because they're like huge binoculars that weigh 70 pounds or something. So you got to be Arnold Schwarzenegger to hold them. Binoculars are a good thing to start with. There's actually a lot of objects out there that are more interesting to look at with binoculars than with telescopes, because they're large, so they kind of fill the field of view through a telescope, and you don't get to see all of it, but with the binoculars you get to see all of it. So that's binoculars. Next will be telescopes. We'll start with the one that most people think of when they think of telescope, and that's a refracting telescope. That's one of these. It's got a big lens up at the front end of it. Light comes down the tube, and it's got a big lens, or a smaller lens at the back end of it, and that is the refractor. Light goes through the tube one time, comes out. Now this thing has, if I can loosen it, something that makes it a little bit easier to view. It's called a diagonal. This thing here. I could put my eyepiece directly in there. Get it in there. There we go. Which, okay, it's not too bad at this angle, but again, if you're watching something, you really want to look at them when they're high up. So let's get this way up in the sky. Looking at something almost straight up. And now, looking through that eyepiece is kind of awkward, to say the least. So, easier, you take this diagonal piece, you put it in there, that goes between the telescope and the eyepiece, and put that in there. It fits in there right. And now all I gotta do is lean over a little bit. And I can look through it a little bit easier there. So the diagonal is just a kind of an aid to observing. It's not necessary. You can use the telescope without it, but it does make it easier to see things through your telescope. So that's the diagonal with an eyepiece. Eyepieces come in a wide variety of sizes. Usually people will have a variety of different eyepieces. This one's got, let's see, that's a 13 millimeter and a 32 millimeter and a 40 millimeter, and this one, 27 millimeters. So they come in all different sizes. The magnification of a telescope is just the focal length of your telescope, divided by the focal length of your eyepiece. So the smaller the eyepiece is, the more magnification you get. Bigger the eyepiece, the less magnification you get. And they also come in lots of different qualities. If you think about it, whenever you pass light through a piece of glass, it tends to separate the colors out. And so if you use a cheap eyepiece, we don't have any really cheap ones, but I guess this is the least expensive one here, about 60 bucks. But if you use a cheap eyepiece, when you look at something like the moon or Venus, what you're going to see is it's got red rings around it, or blue rings around it, or green rings around it. The moon doesn't have green rings. So that's the eyepiece doing that. You can correct for that by putting in multiple lenses. This one has, I think, 7 lenses in it altogether, rather than just, this one has 4 lenses in it. So that makes a big difference in terms of color correction. You see a lot of colors, or you don't see any colors. You don't want to see colors where they don't exist. So, but they do cost more. Obviously, something that has 7 lenses is going to cost more than something that has 4 lenses, and you'll pay for that. This one here, I think this eyepiece here probably costs about $200, $250. This eyepiece here, I think this one runs about $60 or $70, something like that. So they come in a wide variety of costs, but you get what you pay for. So, but that's eyepieces that go with different refractors or any kind of telescope, not just refractors. Go back in there. The telescope itself here is, like I say, it's a refractor, which means it uses lenses, and the opening at the front end of it, let me squeeze it around so I can use it that way. Good, that's high. The opening here is 90 millimeters, like this down with that. See, it's 120 millimeters diameter of the lens up there at the front. So that's the size of the telescope. It's one of the smallest ones we've got out here, but this one also, I mean, this is lenses, so you pass light through a piece of glass, you're going to get color distortions corrected by putting multiple lenses in. This one actually has 2 lenses up here. One of them made out of it's called low dispersion glass, which means it corrects the colors properly, so you don't get a color spread on it. But that does make it expensive. I think they're selling this telescope here, just the telescope, not the finder, not the eyepiece, not the diagonal, nothing but the telescope. I think it goes for about $1,000 for just a telescope. Then you got to put it on something to hold it. You want a nice sturdy mount to hold it. You can't hold it by hand. This one is called an Atlas mount. It's called a German equatorial mount because it was invented by a German. His name was Joseph Fraunhofer, and I guess it's easier to say German than Fraunhofer, so we call them German mounts and not Fraunhofer mounts. It holds the telescope basically with one arm. And if you hold a heavy weight with one arm, you start slowly doing that. And how do you balance yourself? Hold the weight over here. So if you hold the weight on the other side, and that's what these weights are. They're just a counterbalancing weight. So it doesn't grind on the motors. This one also has motors in here. So these axes are able to move. They're motorized, so you can move things along like that, and so forth. Or this one over here moves it like that way. So motorized system is very nice. They're called equatorial mounts because you line up the axis of the telescope either with the equator of the Earth or with the polar axis of the Earth. This one lines up, this axis right here, parallel to the polar axis of the Earth. That's the rotation of the axis of the Earth. So this will move parallel to the Earth's equator, which is what you want to do if you're tracking things across the sky. An object will always move parallel to the Earth's equator. So if you're setting up telescopes and you want to stay on an object for a long period of time, for whatever reason, maybe you're doing photography or whatever, it's going to require you to track. And that means you need to move parallel to the Earth's equator. This is what this one does. This one also has a computerized control system, like this one over here. Same controller, both mounts. But this thing, plugged into the side here, you put power onto it, you can run off batteries or off AC. This is a little computer in here. It's got a database of something like 16,000 objects. And so once it knows what time it is and where it's at in the sky, basically it can find things for you. So you tell it, I want to look at Neptune, and it will move the telescope to where Neptune is. Not that Neptune's really anything to look at, but you can find it that way. So these are very nice. I say though, it's a computer, which means you're going to pay for this. This little controller here by itself is about $500 for just the controller. It's a computer in there, a little microcomputer. So it does cost money for that, but it does make it nice. And these things, like I say, you can hook up a GPS to them, so that will tell it what time it is and exactly where it's at on the Earth, and all you have to do is sync it with what's up in the sky. And the way it does that is it tells the telescope to point at a couple of stars, or it tells you to point the telescope at a couple of stars. And so that's where, it's going to tell you, point at Arcturus. And you scratch your head, where's Arcturus? You go get your planisphere. And the planisphere will tell you where Arcturus is, and you move it over there, point at Arcturus. Or it will want to point at Vega, or Altair, or Deneb, or Betelgeuse, or something else. So you use your planisphere to find those. Once it's done that, you're usually required to sync on a couple of stars. And after that, it knows where things are in the sky. It can find things very easily. So that makes it kind of nice for that. So that's a refractor, 120 millimeters in diameter on a German equatorial mount. By the way, this mount with a computer controller and everything, I think they're selling it for about $1,500. So the telescope and mount together are about $2,500 for this. So, but they're fairly good quality. It's a big, heavy, sturdy mount, so it holds a lot of weight. But that's the refractor. This one over here, the mount is exactly the same. So it too is an Atlas mount, it's a German equatorial mount, got the computer hand controller for it. But the telescope itself is a reflector, which means it uses a mirror. Big mirror in the back end, small mirror up here in the front. So the light comes in, hits the big mirror, bounces up to the secondary mirror, and then bounces back down the tube to where I put my eyepiece. This one too has a diagonal on it, so again that makes it easier to look through. And then it has an eyepiece stuck on it there. So the reflectors don't suffer from color distortions, so you don't have any of that problem. The reflectors do have other problems depending on what their shape is. The cheapest mirrors to make for telescopes are called spherical mirrors. They're basically just a section of a ball. And they suffer from what we call spherical aberration, or spherical distortions. Not all the light focuses at the right point. You can correct that by making it a parabolic shape instead. Parabolic shapes are a little more expensive to make, but it does correct some problems, but then you introduce other problems that are, call them off-axis. If you look at things that aren't in the center of the field of view, they're off at the edge of the field of view. They start to have little tails on them, things like that. And so you get distortions like that. You can correct that by making the mirror a hyperbolic shape. A lot more expensive, a lot more difficult to make a hyperbolic shape, but the Chinese figured out how to do it cheap about 10 years ago, and suddenly there's cheap or relatively inexpensive, I won't say cheap, but relatively inexpensive hyperbolic mirrors available for telescopes. The ones that we use are called Ritchie-Chrétien, after the two astronomers that developed it. Ritchie was the director of the U.S. Naval Observatory, and Chrétien was a visiting French astronomer, and they came up with the optical design, and so we call it an RC. It's a very nice telescope, but it is more expensive. This telescope here, just the telescope, no diagonal, no eyepiece, no mount, nothing with it, just the telescope, runs, I think they're selling them now for about $2,400. So it's more expensive, but if you're going to do photography, those are the best telescopes to use. Most of the big telescopes in the world, like the Keck telescope, the Hubble Space Telescope, of course it's not in the world, but it's of the world. But anyway, they use that same mirror style. It's called a Ritchie-Chrétien design. So it's a very high quality, high design for the mirror. So that's an RC is actually what we call a Cassegrain focus, but the design for it is called a Ritchie-Chrétien or RC. It's a reflecting telescope on a German equatorial mount. This one, by the way, is 8 inches in diameter. That's the size of it, so it's a fairly nice big one. The next telescope we got is a Newtonian telescope. It too is a reflecting telescope. Big mirror down at the bottom, secondary mirror up here at the front. The secondary mirror here is at the flat piece of mirror. And so it reflects the light out to the side where you put your eyepiece. So you're looking on the side of this telescope rather than out the back end of the telescope. Invented by Isaac Newton, who also invented calculus and also universal gravitation and laws of motion and other stuff he did. He did a lot of stuff in optics as well. The Newtonian telescope is a relatively inexpensive one to make. This one uses parabolic mirrors instead of hyperbolic, so it's a lot cheaper. The mount that it's on is called an alt-az mount. Alt stands for altitude, and az stands for azimuth. The azimuth is the angle around, so an alt-az mount. This particular combination of a Newtonian telescope on this type of alt-az mount was popularized by a guy by the name of John Dobson. He was a young man right after World War II who was actually at that point in time, I think he was a monk in San Francisco. He was a little too weird for the monastery though, so they threw him out. But what he figured out is after World War II, of course, the Navy's decommissioning all these ships. And ships have windows, big round pieces of glass. And he thought, I can grind those down to a nice mirror shape, metalize them so I've got a nice mirror. Navy's trying to get rid of all these windows and stuff. They're scrapping all these old ships, so he was able to get them for like 50 cents a piece. And he bought like 2,000 of them and would grind them down and metalize them. And then he would go to construction yards where they have a material that's called sonotube. It's cylinders of heavy cardboard. The cylinders are used to basically make concrete shafts or columns or stuff like that. Fill them with concrete, rebar, and so forth. You let the concrete solidify, and then you carve off all the paper, and you've got a column or a support column or whatever. But obviously, since you're going to tear off the paper, that stuff is not going to be really expensive. And so he would buy this stuff at like 50 cents for a 10-foot length of it. And now he's got a tube, and he's got mirrors that he made, all for $1. And probably about 2 or 3 days worth of grinding away at this mirror and metallizing it. But now he's got a big telescope for like $1 and a couple of days worth of labor. Get some eyepieces, get some cabinetry wood, glue it all together, and the whole setup would cost maybe $5 worth of lumber and glass and so forth, which means you got a really big telescope for really not much money. And so he popularized them, would drag his telescopes out onto the streets of San Francisco and set them up and look at the moon and holler at people, come look at the moon. Hey, come look at the moon. Come look at the moon. Look at the moon. And of course the people would look at him like, you're really weird. What are you doing out here? So, and most would walk by, but every once in a while somebody was, okay, I'll look, and then it would be, oh wow, I can see craters and all this, oh man, that's the coolest image I've ever seen. And so they would get excited about it. And he was called the sidewalk astronomer. He was obviously a weird guy. Who sets up telescopes on the streets of San Francisco in the 1960s. You know, that's the weird age of San Francisco. So anyway, he popularized it. So we call this style of telescope the Dobsonian. And in fact, you can see the name on the side of it here. It's a Dobsonian reflecting telescope. The Dobsonian is just the combination of telescope and mount. The telescope itself is a Newtonian telescope. The mount is an alt-az mount. But when you put them together, we call them a Dobbs or Dobsonian. So very popular for that. This one has 2 finders on it. This one here is basically a small telescope that's just lined up parallel to the main telescope. The reason you want a finder, if you look through the eyepiece of this telescope, you're looking at an area of the sky about that big. Think of the size of that cap held at arm's length. That's the area of the sky you're looking for. So if you're trying to find something in the sky that much at a time, you're going to be searching around for a long time. If you look through here, you're looking at an area of the sky, and I can do this, about like that. And so that's a whole lot bigger area. And so I can search around the sky and find things a whole lot easier. So it's a lot easier to use that. So this is a finder scope, helps you find things. The other one is called a Telrad. It too is a finder, but it has no magnification. This is a small telescope. So it's got a little bit of a magnification. You can see things through it that you can't see with your bare eye. This other one doesn't have any magnification, but it's got a little red LED in there that puts up a set of bullseyes on this piece of glass here. And you look down this way, and you'll see the bullseye in the sky. And you put the bullseye where you want it to be, according to those star maps that we had, the MSA object map, and you're pointed there. Problem with this, though, if you're in a well-lit place like campus where you can see all of maybe 5 or 6 stars in the entire sky, you don't know where to point this because you can't see, we call them the guide stars, the fainter stars that are in the area of the thing you want to point at. You have to be able to see those. If you can't see them, this is kind of useless. But you can see them through this because this is a small telescope, so you can see things you can't see with your bare eye. It's nice to have both of these. We do have a darker place we go to out at the farm, and so out at the farm I like to use these. On campus I like to use this. So we have one of both. You can use them in whatever situation there. So those are the 2 types of finders we have for them. So the last telescope we have, let me put this back on before I lose them, is this one. It's called PST, pissed, because it doesn't work. It does, but only in the daytime. Which means you don't look at stars or planets or moons or things like that with this telescope. Instead, do I get it to point up? And point up that way. And what it does, count that way out. It looks at the sun. It's PST stands for Personal Solar Telescope. It's designed to look at the sun. If you look at the front end of this thing, it looks like a mirror. It's reflecting away most of the light that hits it. So it looks almost like a mirror here. It doesn't reflect away all the light, lets some light through, but right down here there's also a filter that filters out all the colors except for one very narrow range of red. It's called a hydrogen alpha. And hydrogen alpha is one of those absorption or emission lines from hydrogen. And it turns out the sun has fairly strong absorption in hydrogen alpha range, so it's not terribly bright. So when you look at the sun through this telescope, you see a red ball. That's the sun. But you can see things off the edges of the sun because of the way it's working. Works very good for that. So these come in all sorts of different varieties. I think this one here is selling, I think it's selling for about $650 now. Again, that's just the telescope part, no eyepiece with it, no mount with it. This is also a little German equatorial mount. It's only got a motor on it down here. It doesn't have the computerized stuff because if you can't find the sun, you need some new eyes. You know, so, but also, if you think about it though, how are you going to find the sun? You don't want to look at the sun with your bare eyes. So how are you going to find it? Sunglasses ain't going to be enough. You're still going to burn your eyes looking directly at the sun. Even with sunglasses, you're still going to burn your eyes. What do? Look at the shadow of this thing. It casts a shadow on the ground. If it's not directly lined up at the sun, the shadow is going to be stretched out a little bit. So you move it until the shadow is a minimum size. You make the smallest possible shadow you can, and then it's directly pointed at the sun. Then you look through the telescope. Ah, there's the sun. So you can't use the finder scope or something like this. If you put a finder scope like that on there, you would really fry your eye in a hurry. So, little telescopes like this are nice. The bigger ones are obviously more expensive. Like I say, this one I think is selling for about $650. I have one myself that I bought myself to look at the sun. I bought it actually to look at the Venus transit a few years back, and then didn't get to see the Venus transit for various reasons. But I paid $2,400 for it. It's 60 millimeters. It's a big bird, a little bit bigger. But the problem is, you can only use it to look at the sun. That was $2,400 I spent on a telescope that I can only use to look at one thing. I like it a lot, but I can only use it for one thing. Maybe you'll want to do something like this. You can get these things for your telescope. These are called solar filters. You look at them, they're reflecting away most of the light. So most of the light gets reflected away. You put this on the front end of your telescope, and And your telescope is now a solar telescope. You can look at the sun with it. You don't put the finder scope up here. You leave the covers on. You don't use it at all. But you can look at the sun through this. It's blocking 99.999% of all the light, so it's nice and dim. You can see things real well. Then at night, take the cover off and you can see stars and galaxies and nebula and all that other stuff. So this is a lot cheaper. This is only about, it depends on the size of the telescope. Bigger telescope, bigger filters, more expensive. This one runs about, I think about $170 or something like that for this one here. But now I can use my telescope for other stuff besides just looking at the sun. So this is nice to have. So that's all the telescopes. Now, looking through them. Some of you are going to do this tonight when we go outside. Let's see if I can get a picture of the moon here. And let me try again. And let me try again. It just never looks any good. Reason? The exposures you're using are actually relatively long. You may use a significant fraction of a second. And you think you can hold your camera steady for that long. No, you can't. You can't hold your camera steady for 1/10 of a second. You think you can, but you can't. Your camera will pick up little tiny vibrations in there. And so the image that you get is going to be blurry because of that. What you can do, this is a little clamp system that clamps onto an eyepiece. I've already clamped the eyepiece in there. You put your phone in there, like that. And now, let's take this out. Put my, and now I'll give me a little app that delays the photo. So I tell it to take the photo in 10 seconds. So I click, and 10 seconds later it goes, snap, and I get a really nice photo because it's not shaking. Why do you want to delay a little bit? When you touch it like that, tell it to take the picture, that sets a little vibration up. Not much, but a little bit. You want to give it a few seconds to dampen out. And then it takes the picture. So those work really good. This is just a phone clamp. It clamps your phone in there. They make them, this one is specifically for the iPhone. The old iPhones, not the bigger new ones. They make ones for the bigger new ones too. And they make generic ones for any size phone that you can get. This one, like I say, is specifically for an iPhone though. So it only fits iPhone. But the older iPhones, yeah, not the newer ones, but it does a very nice job. Basically what you're doing is you're taking a picture of whatever's in the eyepiece here. So that works fairly nice. You can see things nice. Another thing you might try though, rather than doing your phone, is one of these. This is a webcam. Not the one that's attached to your computer, one that you can do this on. I've just pulled the lens off it. And I get me one of these things. This is called a nose piece. And I screw the nose piece in where the lens used to be. If I can get it in without stripping it. There we go. Screw that in, take my eyepiece out, put my webcam in. That's just a USB. I connect it up to my computer and take a video. If you watch the video, if you take a video of a star, what you'll see is the star is bouncing all around. It's also going in and out of focus. So you get a nice sharp point, then it'll blossom up to a big donut, then back to a sharp point again, then blossom up, and it does that many times a second. So you can get software that will analyze each and every frame of your video, only except the frames that are in focus. And you can see how good a focus you want. Do you want only the most precise points, or do you accept a little bit of blooming up, but not too much? So one in every 100 frames, or one in every 50 frames, or one in every 20 frames, or something like that. And it will analyze each frame, decide which ones are within the focus setting that you've had, and throw all the rest of them away. And then it will take all those that are in focus, and it'll align them on top of each other, and stack them together. And so that 30-second video you took, you throw away 25 seconds worth of frames. That's basically a 5-second still picture that you took at amazingly sharp focus. So you can make a really nice image out of it. The webcams aren't real sensitive, so they're not good for galaxies and nebulas and clusters and something like that. But for planets and stars, they work, or for planets and the moon, stuff like that, they work really well. You can get, I've seen pictures of Mars taken with a little $100 modified webcam. The modification is basically you pull the lens off. You want to get somebody to do that for you rather than yourself, because of course when you do it, you forward the warranty on your camera. So you get somebody else to do it and they sell a warranty with their camera. But I've seen pictures that you would swear that picture was taken by the Hubble Space Telescope. It was probably about a 3-minute video. They only kept about 20 seconds of that 3-minute video. The rest of it was all thrown away. It does take a lot of processing time. Depending on how fast your computer is, it may take 30 minutes, an hour or more to process, but once it's done all that, you can make really nice pictures of that. But like I say, it only works for the bright stuff like the moon planets. If you want faint stuff, you get one of these. Again, this would have come with a lens, although this has been modified so it didn't even come with a lens. But, you take the lens off, you put the nose piece on, and this is a low light security camera. Low light security cameras are designed to take pictures in low light conditions. Hey, that's night in the sky. So again, you take this, put it where your eyepiece went there. The difference now is this has a VGA output, so you have to get a video capture card for your computer. Not a big deal. There's all sorts of video, mostly for gaming stuff, but you can get video capture cards. Same thing then, you take a video, you analyze it frame by frame, you keep only the frames that are in good focus control, the rest of them way, align and stack all the others together, and you got a really nice video, or a really nice still picture. And that one still picture you get out of it, you can get really amazing stuff for galaxies, nebulas, because it will see that fainter stuff. And so you can do a really good job with that. So this is more expensive. The webcam, a webcam costs $50, $60. You get somebody to modify it for another $20 or $30, and you got something for less than $100. This thing, closer to $600 or $700, maybe $800 once it's modified, because they're more sensitive in low light conditions, so they are more expensive like that. But video cams will do a really good job. You can get color ones or you get black and white. This one takes, I think, a black and white. They are selling them now that they will take color pictures as well, but that's a video cam. The next thing you want to do is maybe get you a point and shoot camera. Now, this one has a lens that has a piece attached to it that allows me to screw it onto my camera. Most point and shoot cameras have a thread in the eyepiece, or where the eyepiece is, and now you stick that in there. In this case, I'd want to get a wired or wireless remote for it, and click, click, click. This camera will allow me to change all the settings on it. That's one of the problems with the camera phones, is you can't change the ISO and the exposure times, the shutter speeds, things like that. Although I think they're starting to come out with apps that will do that now, but for a long time they did not have those kind of things. So you were stuck with this thing trying to autofocus, which is only going to see the right things. This, you can set all that stuff on it yourself. Manually focus, because the telescope is going to be what's really focusing on. Do all that stuff, all the settings. You can do some pretty good photography with this. You can sit down with Photoshop or something and play with them, manipulate them, make them look really nice. The typical point-and-shoot cameras cost, I don't know, a couple $100, something like that, for a good point-and-shoot camera. The next level up would be this one. This is called this one's called an SLR, single lens reflex. All the professionals use SLR cameras. You can do that. Take the camera lens off. So you take the lens off, and you put this down before you drop it. You can get a nose piece for it. Put it on your camera. It locks in place. You need to take this ring out now. This is a larger size. With that, my telescope. Get it right down there. Again, you get your wireless remote or something, click, 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 take pictures. We have a class called astrophotography. See my astrophotography people out here? They're all outside taking pictures, because that's one of the requirements for the astrophotography class is you have to do pictures. They're doing lunar pictures tonight, so they're doing pictures of the moon. But we use cameras like these. The school has a few of these cameras. If you are into photography and you want to take the astrophotography class, I encourage you to buy your own camera and use it. The idea here is after astrophotography is over, you continue to do photography of the sky yourself with your camera. So you learn how to do it with your camera in that class. But this is one of the old cameras. This one here is, when did I buy this? 2006, so it's like a 9-year-old SLR. Yeah, that's like having a 9-year-old computer. I got a new one that I bought this summer upstairs. It's mine. Basically, about half of the cameras we have in astrophotography are my old cameras. I'll go buy myself a new one and give my old one to the school, and that will be the camera for astrophotography. Anyway, lots of stuff you can do with these, lots of image processing and stacking. You can run these. You can actually get software that will run your camera through the computer. So your computer controls everything, and you can do all sorts of nice stuff with that. That is the SLR camera. Lens on before I forget it. The last camera we have is the one that's specifically designed for astrophotography. It is a CCD camera. Of course, the CCD camera uses a chip, just like your cell phone has, just like the point and shoot, just like the SLR camera does. The difference is the chip in this one is much more sensitive, and the typical exposure for this camera would be maybe a minute or two. With the SLR cameras, that would be maybe 5 to 7 minute exposure to get the same level of brightness of things. The other thing is this has filters in it. Color filters. This takes a black and white picture. So if you want to take a color picture, you take a picture with a green filter in front of the camera, another picture with a blue filter in front of the camera, another picture with a red filter in front of the camera, and there's actually a filter wheel in here that has all that. So it will automatically switch from one to the other. And then you digitally stack those things together with a computer, so you're stacking your images together yourself to make a color picture. And if you want to make it a little redder than what it was, well, you add a little more red to it. If you want to make it a little bluer, you add a little more blue to it. So you can adjust the color balance there. The camera here works on a chip as well. So that's the same thing. It takes a black and white picture. How do you get color pictures out of this? Every pixel on the chip itself has a color filter in front of it. So you have one pixel that will have a blue filter, one pixel that will have a green filter, one pixel that will have a red filter, and usually there's one of those colors that it's not as sensitive in, so they'll have two of those. They may have two blues, one green, one red, or two greens, one blue, one red, or two red, one blue, one green. Depends on the chip you're using there. But the camera in your phone or the SLRs or whatever will electronically add those 4 pixels together to make one image pixel. So your 12 megapixel camera is actually a 48 megapixel camera. You're cutting that down by a factor of 4. You're adding 4 pixels to make one image pixel. So you're losing stuff. Actually, it's the other way around. The 12 megapixel camera is actually a 3 megapixel image, the way it works. But this one uses everything. The other thing is, I say the exposures are very long. And if you take a picture that's a very long exposure with a regular camera in the daytime, and you look at it, it's got a lot of noise in it. That noise is heat noise. The heat will release electrons in the material. The electrons get collected just like the electrons that are knocked loose from photons of light coming in. And the result is, it's just a kind of a white background on everything. It adds heat noise to it. Most pictures that you take in the daytime, the exposure times are 100th or 1,000th of a second. You don't build up heat noise very much in that 1,000th of a second. If you're doing a 5-minute exposure though, you're going to accumulate a lot of heat noise. The way you get rid of it, cool it. It's got a little fan in there. It's got some hose points that you can attach a cooling line to, run fluid through it. It's got an electronic cooler in it. So this will actually cool the camera chip down about 30 degrees below the air temperature. So lot cooler, eliminates a lot of the heat noise. The higher quality cameras will cool your camera down to temperatures at 40 or 50 below the air temperature. So you can cool your camera quite a bit and make a much better image. So your digital camera can't do that. I guess you could pack your camera in ice, take a picture, but that would be kind of awkward. Might not be good for your camera to pack it in ice. So, but I've seen people that do that kind of stuff for believe me. But anyway, that's the last camera we have. It's designed specifically for astronomical use. And this is much more expensive. Cheap CCD runs about $3,000 or $4,000. A cheap one. They're getting less expensive. When I first started looking at this, this particular camera is about 10 years old. Actually, it's more than that. It's almost 12 years old. Really old. But it cost $8,000 at the time. You can get this level camera now for about $2,000 or $3,000, something like that. So the camera we got for the big telescope, actually we got a bargain on it. It's only a $30,000 camera. So CCD cameras can get really, really expensive. The cameras for some of the big telescopes in the world, like the LSST, is what, several million?
Yeah, it's a fraction of a gigabyte.
Yeah, so it's a significant amount of money for that camera. But CCD cameras can be very, very expensive. Anyway, so that's the cameras, that's the telescopes, that's the eyepieces and finders and all that kind of stuff. So what we're going to do now, there are a couple of telescopes set up outside. Actually, there's what, 3 telescopes? We have 2 Dobbs telescopes like this one, and one that's like that one there set up. We actually have a second one of these that's set up, but the astrophotography class is using it to take some